Let us proceed with static variables first. Now to define a static variable, let us define it here. Static is the keyword. Let's say static int, static, let's say a. Okay, let us assign it a value of 99. Now let us define another static variable, static int static a2. Let's define this one as a1. Okay, let us exit the previous function. Now here, as we had discussed earlier about the variable type, that int, the scope of integer is scope of automatic variable is local to the function, and life of this variable is as long as it is in that function call. So that became apparent to us from this diagram here of the stack. Now static variable, as we know, its scope is again within the function, but its life is throughout the program. So of course, that having said that, we can expect that since a stack holds a temporary variable that changes based on the which function is called and when, so it has static has to be at a different memory location that should be more permanent in nature. So let's see what we can say about static variables. Now let us run this. So since we added new lines, we should compile it first. So we'll compile, and then let us run to the cursor, shift F4. Okay, now let's see what do we have here. Static A1 gets assigned 99 and static A2 is assigned 0. Now note that sum is assigned a value of 24 over here, sum 1, and this sum here is assigned a value of 2. So it is some random value that gets assigned to sum and sum 1. However, the static A1 gets assigned 99 as we did here, and static A2 gets assigned 0. Now the question you would be wondering is it coincidental, or is it just a random value that happened to be 0, or is it always going to be 0? So let us see what happens there. So let's first look at the address. What are the addresses that are allocated for these two static variables? So we add ampersand static A1. So that value is 402000. And what about static A2? 4 ampersand static A2. Now we see here there is some difference here. Now what the difference is, static A2, although it has been assigned after A1, so based on the logic that we had for automatic variables, that it's last in first out. That means whichever variable gets defined last will be having a lower memory address compared to which one is allocated first. So in example here, I'm just revisiting it. A was defined first in main, and hence it gets the highest memory address, and rest variables get lower memory addresses. Now if the same was to apply for static, then A1 should have got a higher memory address compared to A2. Now what is happening here? A1, static A1, is actually getting 402,000 compared to A2, which is getting a higher memory address. So what's going on here, right? As we discussed earlier, that automatic variables are temporary in nature, whereas static variables are permanent throughout the life of the program, and hence it requires a different memory allocation. So these two data types, these two types of memory allocations actually mean different things to the compiler. So A1 and A2, what it says is the difference is actually subtle, and the difference is that the A1 has been assigned a value. Now if A1 is assigned a value, it is stored in a segment that is called data segment. Okay, so it is stored in a data segment, and it's basically a memory location after the text segment. So data segment will store all the static variables that have been assigned a value, that have been initialized. Okay, so here if we see, let's say we have the static variable static A1. Static A1 is assigned here, and what is the memory location? It is 402000. So the memory location for this guy here is 402000. Okay, and then afterwards there is another memory location, memory block, which is called BSS. It's more of a historical significance of this name from when the programming language started. So it's actually from the older time. It is called beginning of I'll have to revisit and let you know what exactly that BSS stands for. Block starting with symbol, that's what it means. BSS, block starting with symbol. And this contains all the static variables that are not initialized. So the static A2 which is uninitialized variable basically gets its memory location at this point, and hence it has a higher memory address compared to A1. Now what the compiler does is it allocates a certain bigger block compared to, so ideally we would expect that, okay, static A1 is an integer type, so we should get 4 bytes allocated for this. But what the compiler does is it stores a bigger chunk of memory for the data segment. Okay, so that is very specific to compiler. On Windows, on different Windows version you can get different memory allocations here. On Unix you'll get a different behavior, but essentially that's the block. So the first set is text segment, next is data segment, and then the BSS, which is block starting with symbol. It's basically a nomenclature that has historical reasons. So BSS basically has all the uninitialized variables. So far we have covered static, and this memory does not get destroyed for the life of the program, and hence that is why all these variables are stored here. Now let's see what happens if we have a global variable. Okay, so global variable basically also gets allocated in the same memory location in the data segment. However, difference is, so let's see what would happen. So for global variable there is no modifier that we would have to add. We can just say int global A1 equal to 999 and int global A2 which will be uninitialized. Okay, so what do you think the compiler would do in this case? So global, once the program executes, it sees global in the very beginning, right? And then it starts seeing the static variable. But what we see from here, there is a big block for data segment, and then there is a big block for BSS. So all the uninitialized static or global variables will go in this memory location, and all the initialized static and global variables will go into the data segment. Now since global is defined even before the function main is entered, hence these variables, the global variables, either if it is initialized in the data segment, it should get a lower memory address compared to the static. So let's see if that holds true in this case. So let's exit this previous program. Stop execution, and then we should compile. And let's run up to this place. Now let's look at what happens to global. So that variable global A1 gets allocated 999, and variable A2 gets initialized to 0, right? Because it is in the BSS section. Any variable that is stored in the BSS would be initialized to 0. Now let's look at the memory locations, what all the values are for these. So F4 ampersand global A1 and F4 ampersand global A2. So what do we see here? So as we expected, the global gets allocated a lower memory location, 402,000. So earlier when we didn't have the global variable defined, it was defined at 402,000. But now that we have the global variable, the allocation will get shifted. So let's see what happens to these variables now. So ampersand static A1, okay, and ampersand static A2, okay. So let's see what happens. So this thing here earlier was static A1, and this was static A2 at 2000 and another location. But now global variable gets the 2000 location, and 4 byte afterwards is the static A1, which is in the data segment since it is initialized, is the static A1 memory location. Similarly for the global variable, in the BSS we get 404070 and 404010. Now again, this is compiler specific, so ideally we would expect that the memory location should be contiguous, as was the case we saw for the initial for the data segment. But here we are seeing that there is a bigger memory difference between the static A2, global A2 and static A2. So this is basically again a compiler specific mode, so it gives a bigger space between these two variables. So this section basically becomes whatever we have seen here is the permanent section. So in addition to code and text/code segment, we also have what we call the data segment and the BSS.